Good evening, everyone. I hope everyone is doing good. It's 7 p.m., so we can start. Can you please confirm if you can hear me and if the screen is visible, the font is okay? Can anyone confirm in the chat? Okay, thank you. Okay, so in this session, we'll be doing the clustering analysis. In particular, we'll be looking at k-means. In your lectures, you went over k-means and how you apply it, but on how you apply it. In this lecture, we'll see two things. Um, what are the different scenarios in which k-means applies and how does it perform? So how does k-means perform in different scenarios? And the other thing would be, how do you apply k-means when you don't know k? K-means expects that you know how many clusters you have. Afterwards, it will decide the shape of the clusters, but you should know the value of k. But what if you don't know k? And what are the situations where you wouldn't know k? So we'll go over these two situations. So let's start by importing our basic libraries. We'll need pyplot, numpy. We need sklearn's k-means. So we can maybe also keep it here for handy. Sklearn's k-means. And we'll take some data sets from sklearn so that we can apply k-means on those. Okay, so let's also specify a few constants. Whenever we create a data set, we'll create 500 data points. For pseudo randomness, let's set a seed. And in case we have a different case, I think this should be enough. Yeah, all right. So let's create our first data set. Let's use something called blobs. It takes number of samples which we have defined. We would like two clusters. Okay, so what exactly did we get? So blobs essentially returns a tuple. In this tuple, you have two objects. So the first one is a numpy array. You would notice this. This is a numpy array, and the second one is essentially a list, or you can say another array, but these are essentially labels. So if you look at the first element, blobs, it has a shape of 500 by 2. That is, you have 500 data points. Every data point has two dimensions, and we can think of them as x and y. Similarly, the other point that you received is a 500 dimensional array, a 1D array. This is essentially your cluster assignment. That is, the first point belongs to cluster 1, the second point belongs to cluster 0, and so on and so forth. So with this in mind, let's maybe write a function that takes a data set and also plots it so that it is easier for us to visualize whether the clustering is working or not. Okay, so let's say we define a function. We say define plot clusters. It takes in this type of data set, clusters, and in case centers are unavailable, we'll define it ourselves. So what do? We can first separate out maybe the x coordinate and the y coordinate. So pull out the x and y coordinates, set random centers if not supplied. If we don't have centers, then we can do this, and then we can just plot the data. So we know that our X value is essentially clusters, the first element, the first column, and our Y is first element, this thing, and our labels are the second thing. So we have this much. If suppose centers is none, then we can maybe just use the first two elements for that. Okay. So I think we also need to know how many centers we have. Hmm. So maybe rather than doing this, if centers are not supplied, don't plot. We can do this. They do something. So this would shift up. We can call this PLT scatter. This is our X coordinate. This is our Y coordinate. Please use, suppose, this marker. And for labels, use this. Okay, so let's see what we have. Yeah. So we have data, something that looks like this. We created two blobs essentially, and they have this standard deviation, and each of them has 500 data points. Okay. So what happens when we apply k-means on these? The procedure goes like this. Let's say modulus k-means, and it takes the following arguments. How many clusters do you need? How do you want to initialize? A number of iterations that you want to run, and so on. So let's see. So in this case, we'll say that I know that I have two clusters. I say that um, initialization is a bit tricky. So the thing is, you can initialize it by yourself. That is, I want you to initialize the initial cluster centers to be, let's say, here and here, and so on and so forth. But k-means is not a deterministic method in that sense that if you rerun it and it randomly picks a point, you will not get the same result. K-means can give you different results based on different initializations. And in some cases, it it can in theory solve a particular clustering problem, but based on the initialization, it gets stuck in a local minima. Therefore, you have these techniques. For example, here you will see it says k-means plus plus or random and so on. If you supply k-means plus plus, what it does is it sort of starts out with one of the data points as the cluster centers. For example, it will pick this as a random data point. When it picks the other cluster, it will essentially try to pick it away from this first center and also while weighing each of the other data points. So essentially, it calculates the distance between these data points and guesses that is this would be a good initial point. So rather than throwing it away like way far away, or maybe in a place where k-means may get stuck, it initializes it intelligently. So that is the other way that you can do it. That is also the default that sklearn uses, this k-means plus plus. Random is again that you pick any random situation, which would be the other case. But this also messes things up because multiple runs can give you different results. So k-means plus plus is good in that sense. So we can use k-means plus plus, and then you will notice that you have n in it. So this is the other thing. So because we said that k-means can give you different results based on multiple runs, n in it essentially says, would you like me to run this essentially k-means multiple times, and then I will return the best result to you. Okay, rather than running k-means once, I will run k-means the first time with a certain initialization and store the results. I will run it again with a different initialization, store the results. The best one that I get, I will return you that. So this is another case that we can get. We can leave it, at auto by default. The other thing is maximum iteration. That is how many times do you want to apply k-means. So in very large data sets, k-means can run for a long time because it can iteratively improve and improve and improve. But if you want to set a cap, you can essentially do those things. And we have other things as well. So if we leave it at this, that is, I have two clusters. I want you to use this particular minimization. Then we just call model.fit. What do we pass? We essentially say, I would like to pass the coordinates of this thing, model.fit. Let's see what we get. Must be k dash means. All right. So we essentially got this thing. And if we would like to get the centers, we can say model dot cluster centers. We just print these, so we get this. So now, because we have these, we can say plot clusters, and we will supply our blobs, but this time we also have the centers. So this is our result. K-means essentially correctly identified that one of the centers should be here, the other center should be here. Now let us look at a few more examples. So this one works. As we can see, this one works. Let's try a different data set. And this time, let's use presets. Okay, so take a minute and think about it. What do you think k-means would do? Where will the centers end and what will the clusters look like? So will it find out this exact same thing, that is this purple thing is one cluster and this yellow thing is another cluster? Take a minute to think about it while I write the k-means algorithm. And rather than maybe doing this, this is essentially the final result. Let's write the code for seeing what happens as k-means improves itself. That is, if I initialize these x's, let's say here, here, and here, how do they improve over time? This will also help us visualize how it works for this. As I do this, think about it. What will k-means do in this case? All right, so I prepared this code for this iterative plotting, so we don't have to go through this. It's just, I mean, boring for that. You can go through it later. So let's see what happens in this case. So we pass to this function k animated essentially your data set and how many clusters do you have. What it does is, as it for every iteration, it trains k-means for a single iteration rather than applying k-means for let's say 300 iterations and getting the final result. For example, this thing, what we do is in a loop, we say, okay, you use k-means, but run it for just one iteration. When we run it for one iteration, we get new centers, right? When we get these new centers, we essentially plot this particular data. That is, this is my current cluster assignment. These are my current centers, and so on. So we get one plot. Once we have done with this one, we do it again, but this time we supply the centers that the previous step output, and we run k-means once again. So k-means improves again, and we get new centers, and then this repeats. New centers, k-means, new centers, k-means, and so on and so forth. And the thing is, we just display this image once, we pause for a while to look at it, and then we repeat. So let's see what we get when we apply, suppose, k-means over, let us say, crescents. We pass the coordinates. We know that there are two clusters. And what else? Initially, our centers would be none. Max iterations, we can set it to 100, and let's leave this at 75. So did you see that? Let's try it again. So this is the ideal case that we expected. That is, this purple thing is one cluster, this yellow thing is another cluster. But this is what k-means ends up to. You would notice that there is essentially an invisible line almost here. Everything left of the line is belongs to this particular cluster. Everything on the right belongs to this particular cluster. Okay, so this is one thing. So why does this happen? So in think about it. How does k-means work? For every point, k-means calculates the distance from the two centers, and whichever is closer, it will assign it to that. So there is no way that, for example, this point here would ever belong to this cluster because it is too far from this x compared to this x, right? This crescent shape essentially is one of the failure cases for k-means because here you're not depending on the distance from your center. It is more of a continuous thing. That is, there is a density, there is a path that the data points are following. So this is one of the cases. Let's try maybe a different data set. We can do, let's do rings. By the way, any confusion with this one? Tanu asks, can you explain how this data will come? Uh, you mean, for example, how I make these data sets or the output of this particular thing? So Tanu, can you elaborate on this? Okay, so moving on, let's create a different data set. In this case, we once again have this many samples. Okay, so this is another data set that we have. So what do you think k-means will do in this case? Will k-means be able to find these two clusters? The purple cluster is the first cluster, and the yellow cluster is the other cluster. Give it some thought. Can k-means do it? And if it can do it, where should we initialize the centers? Will it always find it or not? So while you think about it, I can answer Tanu. So these data sets, for example, these blobs and these crescents, you don't have to worry about them. These are essentially toy data sets that you use to test out your clustering techniques. So these are provided by sklearn. Every in this function, for example, make moons. This they call this a moon, they call this a moon. Similarly, this is a blob. So all of these have certain parameters. For example, this takes factor and noise. Crescent takes something else, it takes noise and randomcy, etc. So these are like off the shelf functions. You don't have to worry about them. As far as this is concerned, that is how do we get this result? We saw, for example, in this case, when we tried to use k-means on these blobs, we just called k-means on this data set and we plotted the final result. This is not the starting result for k-means. Okay, so if we try, for example, our initial thing, even here, k-means animated on blobs. Do we pass anything else? Blobs and clusters. So you would notice k-means improves even in this case. It's not that it already initially starts out here. We do it again. The initial centers are here and then it moves down and down and down. So this is the natural progression of k-means. We just want to highlight this by plotting the whole process. So what's happening here? If we maybe increase, let's say this to 2.75 seconds, you would notice that initially this is here. Now this x will compute the distance to all of the points, and it will see that this point is closer to me compared to this x. Once you essentially calculate a particular cluster, then every point recomputes its distance from the new centers, and then they decide which one is closer to me, and then they update their essentially their citizenship to either cluster. And that is the way k-means progresses. Once you reach a particular point where no data point flips to the other cluster, that is where you stop k-means. We have passed, for example, in this case, maximum, I think we didn't pass it, but you can, in effect, pass this thing, maximum iterations. That is, after this point, I don't want you to check anymore because this is the upper limit. But by default, if suppose even by passing 300, if after 10 iterations, k-means feels that there is no further improvement, it will just stop. So that is what we are doing in this case. So how essentially are we able to plot this? We're saying rather than applying k-means for all of the iterations, just apply it for one iteration. That is a single improvement. Once k-means improves after that one iteration, we have new centers, right? So the next time we run k-means, we are saying don't use random initializations for your centers, use the previous output. The previous centers, use it to initialize your center. So we are sort of artificially making it run k-means for multiple iterations by ourselves manually passing these centers. That is why we are able to see the progress of k-means over these iterations. Is that clear? Okay, so let's think about this one. So the previous case, it was not a circular data set, so maybe that's why k-means did not work. But what about this one? Both of these are circular in nature. So let's try it on this. Let's say we have k-means animated and we pass these rings and we know there are two clusters. And maybe we should drop the time. So notice that k-means is barely improving. Maybe just a few, 1 or 2 points are flipping, but more or less it has once again split the plane into two parts. This invisible line you can see. So this essentially happens because of the way k-means works, because of its use of the distance function. When this x computes its distance essentially along these points, all of these points, for example, this yellow point is barely, just by a bit, by a hair's length, it is closer to this x compared to this x. Therefore, this belongs to this one. But this other purple point is closer to this x, therefore it belongs to the lower cluster when you apply k-means. But this is not the correct of obviously solution, right? You would need something, you would need essentially a different technique that you would use. You should think about whether the hierarchical clusterings that you use, for example, the agglomerate U or the other one, can they identify these things? Can they identify the crescent or the rings thing? You should think about it after the lecture. So let's try a different one. We have done crescents, we have done rings. Let's do this. We have datasets dot. Let's again use blobs. So we know it works on blobs, right? We tried it on blobs. It works here. So let's try a different thing. We have, we make blobs. You have two centers. Look at these two data sets. You can see that they are essentially two, right? The yellow one is one. I mean, even if I did not color them, you would maybe be able to see. So if I remove the coloring, so if suppose we don't pass this, you can still sort of make out that there is a denser part in this area and there is a scattered part in the other area. There are still two clusters essentially, right? So maybe we can use a different seed if this one is too overlapping. Yeah, maybe this one is better. So there is a clear, I mean, separation in this case. So if we color this once again, we can collapse this. So what do you think? Will k-means be able to do this one? Okay, so let's try k-means so and see what we expect. So we expect essentially because k-means works on circular globular data set. So this is a globular data set, this is a globular data set, and we know that there are two data sets. So I mean, sorry, two clusters. So let's see what happens. So if we have k-means and we, let's call it varying density. Maybe varied density. Okay, so the colors are flipped, but essentially it is able to do it. So how do we, maybe let me increase this one further. Yeah, maybe this one would be a better example. Yes, maybe this is a better example. So in this case, we see that, I mean, this purple points are very tightly bound clustered, but the yellow point is essentially scattered, and we expect that k-means should be able to find this one. But what happens here is that k-means again has this invisible line where some of the points are stolen by the dense cluster. When we had, let's say, a smaller density, we were not able to see this effect because they are fairly far apart. So essentially, it gets away with it. But if essentially these things are a bit closer, for example, like this, then k-means struggles in this case. So even though the data sets are blobs, they are globular in nature, that is, they have this round structure. So we don't call them like circles or spheres because you can have multi-dimensional data where you essentially call them a glob. Okay. So even in this case, the only problem is that they don't have identical density or similar density. So one is much dense and the other is much sparse. And because of that, k-means once again struggle. So this is another failure case for k-means. Okay, let's try one last data set. We can do, so this one was same size, different density. Let's do same density, different size. We can say varied size is data sets dot make blobs. And this time we're saying I need different samples for different clusters. So we will take, let's say, 0.1 times the number of samples for the first one and 90% of the samples for the other one. And we can maybe use an integer function here. So this is the first one. And for the second one, we'll use 90% of the number of samples. So 10% and 90%. So the purple one will get 10% of the nodes. The other one will get the full thing, but same density. So we have this, our cluster STD. We can set it identical for both of them. So this is a cluster density of 2. This is also cluster density for 2. And again, we can use some random state. So let's use seed and see what happens. So plot clusters, varied size, and we can use this. Invalid syntax. Why is this invalid syntax? Because integer 0.1 number of samples, 0.1 number of samples. So maybe this is too close. Let's try a different seed. Mm, nah, this is almost not 2 clusters. Let's try with this one. Let's see what happens. Yeah, this one works because they are too far apart. Yeah, so gets away with it. How many samples are we using? 500? Yes, 500. So in this case, it works, right? So in this case, essentially what happens is, for example, these points, it just computes the distance between them. So because density is not involved, it doesn't matter that one cluster is bigger or smaller than the other. The distance matters, not the size of your cluster. Okay. In this case, the previous case, what happened was they had equal size. That is, this one has 500 nodes, this one has 500 nodes, but these are densely, they are packed together very close to each other, and these points, even though they are not close, I mean, to these points, because of their distance, they get assigned to that cluster. In this case, this cluster is much smaller than this cluster, but because they have similar density, k means works on this case. So this is a good case for this one. Okay, so you can also so suppose you come about such data in real life, how do you essentially process these particular clustering algorithms? The answer is there are different techniques. For example, you used hierarchical clustering. There is another technique which is called density-based clustering. In density-based clustering, what happens is, for example, this X, if you initialize it, for example, here, rather than expanding based on distance, it expands based on density. That is, it says, okay, I see data here. It will essentially crawl like this. So this data will become one cluster and this data will become another cluster. In the density-based techniques, for example, there is one which is called DB scan. I don't think it was covered in your lectures. The way it works is it identifies, let's say, a particular point as a starting point, and it says within a particular radius, do I see another data point so that I can extend the data set, extend my cluster in that direction. So suppose you find a lot of data in this side, so you go this way, this way, this way, and you keep on incrementing. Suppose you are here, it sees that there is this, even though this data is here, it says it is not, let's say, in this radius for me to jump to this one. So it will not catch it on to this particular data set. So it will keep on going in along this moon direction and land up here. Similarly, this one, it will create its own cluster here. It will also work on the rings, because even in rings, it will essentially start expanding, expanding, expanding till it covers this one, and this one will expand independently like this, and it will not jump. But density based, I mean, they have their own shortcomings. So if you want to go over that, you can see sklearn clustering comparison. So I hope this is visible. You see something like this. These are the different clustering techniques like mean shift, agglomerative clustering, DB scan, optics, etc., etc. So we tried some of these. So for example, look at this crescent thing. In k-means, this crescent did not work, but DB scan, it is able to identify this thing. K-means struggled with these rings, but DB scan is able to work with these rings. Similarly, if you have, let's say, this data set, you have different densities, you have a tightly packed cluster and a big cluster. DB scan essentially works here as well, and you would notice it also has some black points. So DB scan doesn't have to assign everything to a cluster. It can say, hey, some points don't belong to any cluster. They are just noisy points. K-means will assign everything to some cluster. There is no concept of noise in K-means. Okay. So I think this would be useful to keep this in mind if you ever require it. These different clustering techniques and how you can compare them. Hmm. So now let us look into another thing. In all of our cases up to now, in all of these cases that we have visualized, we knew how many clusters there were because we were able to plot the data, right? We have these two things. We know intuitively that there are two things. This happens because our data is essentially, our data is two-dimensional. If you just even go for crescents, let's say, you see 500 data points, 2D. But suppose you have more data, let's say four-dimensional, six-dimensional, then you're not able to plot this data set. Because you're not able to plot it, you have no idea how many clusters there are. So how do you initialize K in that sense? There you have to use a technique called the elbow point. Okay. Has this been covered in your lectures, the elbow method? Yes or no? Okay. So if it hasn't been covered, the idea here is, let's first start with some data. I'll explain it along the way. Okay. So suppose we once again make these blobs. Let's use, let's say 1000 samples. And rather than using two features, let's use 10 features. So our data is 10 dimensional, so we cannot plot it. Let's use four clusters rather than two clusters. And our standard deviation is, let's say, one, and we set some random state. Okay. And we have this. So here, if we look at the shape, it is 10 dimensional. If I were to supply it to, let's say, our blobs, it will still plot it. Okay, it still plots it somehow. But this happens because the way we have written our code here is that use the essentially the first dimension for your x coordinate and the second dimension for the y coordinate. It happens to be that they are enough to differentiate the four clusters, but in very, I mean, it need not be the case. And it can also give you spurious clustering, because two dimensions can give, let's say the first two dimensions give you some clusters. The third or fourth can give you a different set of clusters. Fifth and sixth can give you different clusters. So we should essentially include a check here. That is, if clusters, if clusters zero dot shape, in fact, wait, but shape one is greater than two, we should raise an error. We can say maybe we can raise a value error saying data shape, say only 2D data can be plotted, and maybe we can just print it here. Okay, so let's try this again. Okay, only 2D data can be plotted. So in this case, we cannot plot it. So we know, I mean, because we created the data, we know that there are four clusters. But suppose I just gave you this data set randomly and you just saw this text. That is, you have this thing and you have no idea how many K, I mean, what to set for K. So the way you do it is something called the elbow method. In elbow method, what you do is you start out with K equal to 2, or maybe even K equal to 1, okay? And then you apply K means, all right? When you apply K means, you after that calculate the distance between the cluster center and its members. Okay, so for example, in this case, this x calculates the distance to its thing, this x calculates the distance to its members, and so on. And then you take the average. Take the average. Okay, so you're taking the average of all of the distances between the members and its points. Okay, so this gives you some estimate of, I mean, of your k means. You plot this point, this average. You plot it. Okay, once you do that, you increment k. Now set k equal to 2, and you repeat. You apply k-means, calculate the distance, take the average, plot the point. Then you do k equal to 3, k equal to 4, and so on. I mean, for whatever reason, let's say you go up to k equal to 10. So you expect that your curve will essentially change as k increases, and let's see what it looks like. And then I'll tell you why is it called an elbow method. Okay. So suppose we have created this 10-dimensional data. So what do we do with this? Let's look at k-means, and there is something called inertia. Yep, inertia. So notice inertia is essentially the sum of square distances, samples to their closest cluster center, weighted by the sample weight. So this is essentially the same thing that I told you. Um, I shouldn't have deleted. Yeah. So essentially, you apply k-means, you calculate the distance from each of the cluster centers and its members, and you take the average. This inertia is essentially the same thing. Sum of square distances, samples to their closest cluster center, and then you essentially average it. So this thing, once k-means is trained, it can return this thing to you, inertia. And you essentially want to plot this point, this inertia point. So let's see how it happens. We can say for k in range, let's say we start with 2 and we end up at 8. Okay, we can also do 10, but let's say we go up to 8. We have to train k-means. So we'll say k-means, I want the number of clusters to be equal to k. I want you to initialize using k-means plus plus, as we discussed earlier. Do a single iteration. And by the way, this is not iteration, just like a number of initializations. I don't want you to run k-means again and again and give me the best result. Just use a single initialization and be good with it. We would like to use 300 iterations at, let's say, some random state. We can call it seed. We can also break it like this. Okay, so we have this k-means. We can call fit on it, k-means dot fit, or we can call it inline, and we pass in blob 0, right? This thing, blobs 0. So we have k-means, and then we can store the inertia. So we can maintain a dictionary, and we can say inertia k is equal to k-means underscore k-means dot inertia. So when we run this, if we print our inertia scores, we have this. When we use 2 clusters, our inertia was this much. When we use 3 clusters, the inertia was this much, and then it essentially changed. So let's see if we can plot this. We have blt.figure, blt.plot, keys, inertia values. We can use a marker, and our X label is the number of clusters, which is K, and our Y label is inertia. We can say plt.show. So do you see that? Do you notice that this looks like an elbow? This is essentially your bicep, and this is your forearm. And this point, 4, is your elbow point. And you would notice that this is what we initialize it with. C equal to 4. So in an elbow method, when you get this plot, this point, this elbow is essentially your best possible guess that this is the number of clusters that my data has. So what happens here is that when you use just 2 clusters, for example, the inertia was too large. It was 70,000. Then you went to 3 things, and the inertia, which is essentially the distance between the cluster centers and this, it drops further. But beyond 4, because when let's say you already have these 4 clusters, if you subdivide these 4 clusters, you don't improve that much. So there is still some improvement. So after 4, the value has dropped. So if you notice here, like 99,500, 9,300, 9,081, the value is still going down, but it is not drastic. So essentially, this point gives you the best possible result, and this is called the elbow method. Is that clear? Should I repeat anything? All right. So let's go over one last thing. Suppose, mm, suppose we create some data. It's also called whitening to some extent. Let's use three maybe. So let's say we have these three blobs, but rather than giving you this data, let's say I give you something else. So now we have this data set. This is essentially the same as this. We have just transformed it a bit. If you apply k-means on this data set, you will get the perfect results because these are globs, they have similar density, and they are cleanly separable. But if you were to apply k-means on this, what type of result do you expect? So let's maybe even try it. We have k-means animated. We pass transformed. We know there are three centers. Okay, so this is the final result. If we were to apply it on the original, in the original, we get clean clusters. In the transformed case, we get this clusters. Suppose I did not tell you that I am giving you a transformed data set. Suppose this is the only thing you receive, and you apply k-means and you see, oh, this is like a gone case. I cannot apply k-means on this thing, right? But the thing is, there is something called whitening a data set. That is, you can transform this data set into a format that k-means can work with. Okay, so essentially what you want to do is you see that these are sort of stretched globs. At the end of the day, these are still globs, but they are just stretched. So is there a way where I can remove this variation in this direction, so that they become sort of these globules? So the thing is, there is you can use SVD for that. So if you're familiar with like linear algebra, you would know SVD, but for the time being, if you don't know, so SVD is just a technique that is given a particular, let's say, space. So this is like a two-dimensional space. It identifies the direction of this maximum variation, and it gives you these directions individually. So it will say, okay, your maximum variation is in this, your second most variation is in this. So the more dimensions you have, it will give you this I mean, essentially thing. You can search it as well. So SVD, you can read about it later. Singular value decomposition. Okay. So suppose we were to apply it here, what will it give us? So this is just for your practical usage. Maybe this is not covered in the course, but suppose in real life you get these data sets, you can use it. So what you can do is you can apply and you can pass it this. So you see, this is our data set. When you apply essentially SVD on that, it breaks your data, for example, X, into these three matrices, U, sigma, and this thing. This sigma, if you print it, this is essentially a diagonal matrix, and the values essentially tell you this the scale of your variance. And these capture, for example, the vectors, the directions of this thing. So when you use this, you essentially, I mean, you can look at it up later, but I mean, this is just for your convenience. That is, These three data sets, which were initially non-separable by k-means, by using, SVD, you can turn it sort of into globules. And suppose if we apply k-means animated on this one, let's say on SVD with three clusters, k-means is able to separate them, you can notice in this case, rather than here. So this is not that different from this. These are still stretched globules, but there is just a slight improvement so that k-means can work. Okay. So to summarize our lecture, we started out with applying k-means to a standard globular data set, and we saw that k-means works well. Then we went on to see, are there some data set where k-means can fail? And we saw that if your data set has, let's say, dense parts and that are non-globular data sets, like non-globular clusters, in fact, suppose these crescents, k-means fails and it essentially partitions your space into two parts which are equally divided. Okay. We also saw that even if your data set has a circular shape, if they are overlapping, or for example, you cannot cleanly cut them with a line, k-means struggles even in that case. It essentially cuts the plane into two. Then we saw that, okay, let's use two globular data sets. The only difference is that one is dense and the other is sparse. What happens in that case? Even in this case, k-means cuts the space into two, and essentially your two centers, they have a line exactly at the middle. It essentially, what do we call it? It equally divides the plane between your two centers, and it doesn't matter. Your sparsity doesn't matter. Then we saw the fourth case, that is, suppose you have different number of data points, but they have the same density. In that case, k-means was able to work. That is because essentially, since density is not a factor, so distance is not a factor, so k-means can work in that case. Then we saw, okay, suppose we have a data set where we cannot plot the data, and so we don't have a hunch of how to set the value of k. We went for an elbow method. In elbow method, you plot essentially the inertia for different values of k, and you notice the elbow at a certain point. The elbow point is your best guess for the value of k, and you go ahead with it. The final thing is, sometimes you get data set that initially, even if you are able to plot it, then you think that maybe k-means is not the right algorithm here. But if you whiten the data, that is, you remove the excessive variance in a particular direction, you are still able to apply k-means in those situations. Okay. So if that is clear, then we can end the lecture. You will find the code at this particular repository. We have previous notebooks here as well. And the lecture itself, you will find at this YouTube playlist. Okay, so I'll paste the link in the chat, and I hope this is helpful. Let me stop recording.